Hey folks, and welcome to 8.2. This section of the fluids unit is the more exciting one, I think. 8.1, you really just relearned density and pressure in terms of physics instead of chemistry ideas. And in this unit, you put that to use. And so 8.2 is divided into two sections. The first part is about buoyancy and the buoyant force, and what happens to fluids, how do fluids behave when they are static or at rest. And then the second half, the bigger half of 8.2 is we talk about Bernoulli's principle and basically what happens to fluids when they flow. So we'll start with a definition of the buoyant force and an explanation of like what it is and where it comes from. So the buoyant force, which causes buoyancy, causes objects to tend to float, is an upward force, it's really a net force, acting on an object in a fluid that equals the sum of all the forces applied by the fluid surrounding the object. So in this little diagram, I want you to imagine that this is a three-dimensional object, so it's a cube, and it is submerged in this fluid. And so the way pressure works is pressure is exerted on all sides of an object, on all surfaces equally. Not equally, sorry, on all surfaces. So there are 4 arrows that I drew, but there's really 6 arrows representing pressures. Now, what we learned in 8.1 is that the pressure in a fluid increases with depth, right? So we have this equation that helps us describe the absolute pressure of something based on the pressure at the top and then the pressure difference as you go down. And so what we end up seeing is like, because the left and the right hand side are symmetrical, right? They're like each section of that wall is at the same depth. The pressure at the left side is equal to the pressure at the right side. And so that's, there's no net force in the left or right direction because of that. Same thing happens to the forces that are exerted on the front and the back. We can't see those arrows, but the pressure exerted at the front of this cube is equal to the pressure exerted at the back of that cube. And again, same thing with the symmetry. Even though the pressure is lower near the top of the cube and higher at the bottom, it is symmetrically divided. And so there's no net pressure at any point along the front and back faces. However, again, because pressure does increase with depth, the pressure exerted on the bottom has to be greater than the pressure exerted on the top. And so it's that difference in pressures that actually causes what we know as the buoyant force. The buoyant force is essentially, as it says, the net force due to the fluid. And so that is going to be equal to the force exerted on the bottom minus the force exerted on the top. And so we're just going to explore what that looks like as it depends on the properties of fluid. And this idea of the buoyant force comes from Archimedes' principles. It's a very old idea. The buoyant force is equal in magnitude to the weight of the fluid displaced by the object. So you learned about this when you studied chemistry, but basically like when you put one object into a fluid, it has to move that fluid out of the way so that it can exist inside the fluid. So it displaces a certain amount of fluid. You would notice that as like the amount that the water level rises, that's equal to the volume of fluid displaced. And that's how you work with density in chemistry. So this like the weight of the fluid displaced represents our buoyant force. So we can write that out. FB for buoyant force, and then the weight of the fluid is going to be the mass of the fluid times G. I will try and be consistent and use the subscript F for fluid and the subscript O for object. And so this is like just a pure definition that the buoyant force is equal to the weight of the fluid, so that's the mass of the fluid times G. To get a little bit more expansive and deal with some of the variables that you thought about in 8.1, since density is equal to mass times volume, we can write that out as an object's mass is equal to its density times its volume. And so if I insert that into the buoyant force equation, I get that the buoyant force is equal to the density of the fluid times the volume of the fluid displaced times g. And so that is the buoyant force equation. Now that's written in your equation sheet. It does not have the subscripts, but I highly recommend that you keep using the subscripts regardless of what's written on the equation sheet, because it is so easy to get confused between the density, volume, and mass of the object in the fluid and the same values for the fluid itself. So that's kind of the end of the video, but I have some important considerations here that I want you to understand. The buoyant force only depends on properties of the fluid. And this might make sense, right? So the buoyant force is due to the fluid, and so depending on the density of the fluid, it might be able to better push up an object or not. It does not depend on the depth within the fluid. Now that mostly just has to do with the fact that there's like a linear relationship between the pressure at a point and the pressure and depth. And so as far down as you can go, even resting on the bottom of a container, the buoyant force is still going to be equal to the weight of the fluid displaced. Or it does not depend on the composition of the object. So what's interesting about that is like whether the object sinks all the way to the bottom or hovers in the middle of the liquid, or the object actually floats on the surface of the liquid or the fluid. That doesn't influence the magnitude of the buoyant force. It's really, again, just how much of that fluid was displaced and what is the weight of that fluid that was displaced. The last part is going to be generally the most confusing part. We have two words that can describe objects sitting in fluids, either floating or submerged. Floating just means that some part of it is above the water, whereas submerged means that it's surrounded on all sides by the water or the liquid itself. So let's start with the object being submerged. If the entire object is within the fluid itself, that means that the volume of fluid displaced is equal to the volume of the object. Now that's the easiest way to deal with the buoyant force equation, is if you get to use the entire object's volume as the fluid's volume that's displaced. However, if an object is floating, then only the amount of that object under the surface of the water counts toward that volume of fluid displaced. This part of the object up here is not displacing any fluid because it's not submerged in the fluid. In this case, the volume of fluid displaced is less than the volume of the object. So you just want to keep that in mind as you work with the buoyant force equation, and we'll do some problems in the next video.